All right, welcome back. We're going to be discussing the Robinson annulation, which is a two-part reaction. One part we've already learned, that's the aldol condensation. And the next part you may have seen before, but it's definitely worth recapping. And this is the Michael reaction, sometimes called Michael addition, or even what we call conjugate addition. So you may have seen this depending on what you learned during your organometallics or SN2 prime reactions, but nonetheless, we're going to introduce it here, and you should be totally good to go on understanding what conjugate additions are. All right, so this often happens between an alpha beta unsaturated carbonyl compound, and this compound would be sometimes called the Michael acceptor, and an enolate, which is nucleophilic and would be called the Michael donor. All right, so what we're going to look at is two very common Michael acceptor donor pairs, and one of those is called methyl vinyl ketone, or for short MVK. All right, and this is going to be a good Michael acceptor, or an alpha beta unsaturated compound, specifically carbonyl. All right, and again, we have our carbonyl right there. All right, and this is alpha, and that's beta, and we have a degree of unsaturation there, also known as a pi bond or a double bond, but nonetheless, we call these alpha beta unsaturated carbonyl compounds, and they are good Michael acceptors. All right, for conjugate addition, or the Michael reaction. So another reactant that we see a lot is something that is easily enolizable, and that is something called diethylmalonate. All right. And this is a good Michael donor. And it is easily enolizable, which is ready to go for the Michael reaction. All right, so let's go ahead and start working on the mechanism between these two compounds to give us a Michael addition product. So the first one is going to be the generation of the nucleophile, or in other words, generation of the enolate. Nope, don't need that. There we go. Okay, so diethylalonate here. What did I just say? Diethylmalonate, pardon me, has an alpha position here. All right, it's between two esters, so it's quite acidic. And if I take something like ethoxide, now again, I want to do my base matching, I can easily generate this enolate. And it's practically irreversible. All right, so now we have our enolate. And the second step is that the enolate is going to Michael add to alpha beta unsaturated compound. So let's go back to our enolate. And we had methyl vinyl ketone in the previous reaction scheme. So we'll go ahead and draw that. All right, so we have our alpha and our beta. Okay, and now we're going to do that. All right, so why does it attack the beta position rather than the carbonyl carbon? Well, this comes back to what we may have seen before with conjugate addition, and the hard soft acid base theory kind of helps us figure out whether we're going to get what we call Michael addition, where you attack the beta carbon, or the carbonyl carbon. In the case of this enolate, they are soft nucleophiles, so we're going to get attack at the beta position. All right. If you were to use something like, phenyl lithium, which is a hard nucleophile, you would expect attack at the carbonyl carbon. All right. But an enolate is a soft nucleophile. All right. So we're going to get attack at the beta position. And the way this is going to look, all right, what are we making a bond? So what I'm going to call this guy is my nucleophilic carbon here, Nu, and it's going to attach to the beta carbon. All right, so let's redraw that. So here's Nu. All right, and it attached to beta. All right, now beta used to have a double bond to alpha, but now it's just a single bond. All right, and alpha is bonded to the carbonyl carbon with a green dot, if you will. Okay, and then that carbon is attached to a methyl group. Okay, so we have an alpha carbon that has a double bond to the carbon with the green dot, and nope, we don't have a double bond there, sorry. And we have our O minus. All right, so we have now an enolate system here, and what's going to happen is, remember the ethoxide from the first step that was used to generate the enolate is in the conjugate acid form ethanol, and now what we're going to get is collapse of this guy to give us that ketone system on the end there. All right, so what we've done is we've had conjugate addition to our methyl vinyl ketone. All right, so this is essentially Michael addition here. So now what I want to do is take Michael addition and add it into a reaction that we've seen before. That's the aldol condensation. So this reaction is quite complicated, and it's probably going to be the most complicated one that we see in all of organic 2. And it's a brilliant reaction. It really opened up the avenue into synthesizing a class of compounds, the hormones, if you will, or the steroids, and it really opened up synthetic chemistry into endocrinology. So, and it was developed by a fantastic chemist from England named Sir Robert Robinson. All right, so it bears his name, the Robinson annulation, and that's a U there. So let me clean that up. So remember earlier I said something about an annulation, right? This is a ring-forming reaction from an intramolecular reaction. So annulation, so we're going to be expecting to form rings here, all right? So what this does is it's going to form rings by taking the Michael addition, combining it with aldol condensation. All right. So I want to show you how it works through the mechanism, and then I'm going to show you the shortcut on how to predict how the reaction works. And the key to getting this guy right is using the right labels on your Michael donor and your Michael acceptor. All right. So let's take a look at an overall reaction. I'm going to take methyl vinyl ketone again. And I'm going to take a ketone there. So I have a methyl group up here that I'm having trouble drawing. There it is. All right. And what I want to do here is go ahead and kind of get my labeling system done here. All right. So when we look at the alpha beta unsaturated ketone, the first thing that you want to do is label alpha and beta. All right. Whenever you see an alpha beta unsaturated ketone, we're going to be talking about Michael additions in the Robinson annulation, so we need to label those guys. But let's be specific and call this guy alpha 1. All right. On the other side of the carbonyl is what we call alpha 2. All right. So we've labeled everybody that's appropriate on MVK. We need alpha 1, beta, and alpha 2. Now, on the other compound, we're going to be doing a Michael addition, all right, in the first step. So if MVK is our Michael acceptor, which means it's going to be attacked by an enolate, well, whatever this guy is over here, the cyclohexanone, if you will, that's going to be our Michael donor, and it's also going to be our enolate and nucleophile. So we need to generate an enolate. And again, we're going to be doing this with ethoxide, right, or hydroxide, either would work in this case. But it's going to be thermodynamic conditions. So what we need to do is we need to figure out where our enolate is going to actually be attacking from, all right? And since it's thermodynamic conditions, we're always going to form the enolate on the more substituted side of the ketone, and that happens to be on this end here. So what I want to do is I want to label it with the letter N for nucleophile. All right. So this carbon, I'm going to kind of highlight it in green. That is our nucleophilic carbon in the first step. All right. The last thing that we need to do before we go any further is we need to label the carbonyl carbon on the attacking enolate as E, which means it's going to be an electrophile in the second step. So in the first step, the guy with the N in the E, first step in a Michael addition, carbon N is going to be a nucleophile. And then in an aldol condensation, carbon E is going to be an electrophile. All right, so the molecule is going to kind of be bipolar. All right, at the beginning, it's going to be nucleophilic, and at the end, it's going to be electrophilic. And we'll go through the mechanism and show you that. But what I want to do is use this I guess, labeling to show you how I like to show these guys getting connected. All right. So what ends up happening here is we're going to form a ring. All right. And before we go through the mechanism, I just want you all to bear with me. All right. There's one ring. Okay. No major changes except that the carbonyl is no longer there. And then there's N and E. So this is kind of how we construct it. Now it's going to be a little confusing because we haven't seen how this works. But then we form a second six-membered ring fused to this guy. And what's going to happen is we said that this guy's a nucleophile in the first step, all right, the N, and we're getting a Michael addition, so it's going to make a bond to beta, all right? That's the definition of a Michael addition. And of course, beta is attached to alpha 1, and then alpha 1 is attached to a carbonyl, and then the final thing is that we're going to see a pi bond being formed from the aldol condensation at the final step between alpha 2 and the electrophilic carbon. Now, that probably made absolutely no sense because we haven't looked at the mechanism, but I want you to have this as a reference. So when you're asked to react a Michael acceptor and a Michael donor and show them reacting to give a Robinson annulation, you can use this labeling to get you to the correct product. All right, so with that said, we're going to go ahead and move on to show you how this reaction would possibly work. All right, so strap in and let's do this. Okay, first step is the Michael addition. All right, we saw that in the, at the beginning of this presentation, but nonetheless, it's worth going over again. So we're going to have to make the enolate first. All right, so we're going to react our ketone, not methyl vinyl ketone, right? That's not going to be our enolate that we're forming. The methyl vinyl ketone, the alpha beta unsaturated ketone, that is our acceptor. So we need to make our donor first, or AKA our enolate. And the way we're going to do that is with ethoxide. Right, there's a hydrogen at this alpha position. That's the more substituted position, and since we're dealing with thermodynamic conditions, that's where we're forming our enolate. All right, so we form this enolate. And now what we're going to do is we're going to attack MVK with enolate. All right, so I'm going to draw MVK. And I'm going to draw the enolate. Okay, it's probably worth going ahead and labeling everybody the way we should for good Robinson annulations. Here's N and there's E. Okay, so the N, of course, means that's the nucleophilic part of the molecule at the beginning. And here's alpha, we're calling it alpha 1, and beta. So how do I know the difference between alpha 1 and alpha 2? It's really just trying to help us do this roadmap. But again, just call the alpha and the alpha beta unsaturated system alpha 1. Over here we have alpha 2. All right, so now we're going to do our Michael addition. Okay, so enolate collapsing to attack the alpha beta unsaturated ketone by using carbon N. So what do we have here? All right. So let me move B over a little bit. Looks like it's kind of in the wrong place, because it is in the wrong place. Okay, back here, there's beta, and beta is attached to N. There, that's better. See why it's good to keep these guys labeled? Easy to make a mistake. All right. And we need a double bond between where? Alpha 1 and what was the carbonyl carbon. Okay. All right. And we have ethoxide that was used in the first step to make ethanol. So now what's going to happen is the enolate is going to go back to the keto form by grabbing the hydrogen from ethanol in this case. All right. So what I'm going to do on the next slide is redraw our reformed ketone. So it's alpha 2, alpha 1, beta. This is N and E. All right, and we have ethoxide. And what we're going to get here is alpha 2 is now going to become enolized. All right, so we're going to grab the proton off of alpha 2. We have N and E. And now we're going to get an intramolecular aldol reaction. All right, so this enolate is going to attack E. So this is why we labeled this guy as E, because it becomes electrophilic in the aldol step. All right. So now we need to figure out what we've got going on here. All right. How many carbons are in this new ring? So there's one, there's one, there's one, and there's one. All right. And of course, it's going to make a bond to E. All right. So this is going to give us a new six-membered ring fused on here. All right. So let's be careful. There's N and there's E. Okay. N is bonded to beta. Beta is bonded to alpha. And then we have a carbonyl, right? Because the O slammed down and made a double bond. And adjacent to that carbonyl is alpha 2. And then, of course, alpha 2, we're showing correctly, attacked carbon E. And carbon E will have an oxygen out here that is an O minus. All right. So again, ethoxide was used, it looks like 2 steps ago. So we have ethanol. And ethanol will serve as an acid to make what we're calling our penultimate molecule. So penultimate's a really fancy word for saying second to last. All right. So there's N, E, beta, alpha, alpha. So this is 1 and 2. All right. You may recognize this compound. This is an aldol. All right. So aldols, in the presence of base like ethoxide, are going to collapse to give us aldol condensates. All right. So this is our final step. So here we go. Right. The base will grab that hydrogen in the alpha position. We'll make a double bond between alpha 2 and E and kick off hydroxide. All right. So this is an aldol condensation here. And we will finally get our product. There. That's it. Okay. So going back to our labels, there's N, E, alpha 2, alpha 1, and beta. All right. So getting those 5 carbons labeled is paramount to getting this reaction solved effectively. All right. So it's a very beautiful reaction. Many of you are probably thinking, yeah, right, that's a lot of steps. But again, the steroid world, a lot of the human hormones, or any kind of hormones really, are based off of these ring systems that look like this. All right. They have these 3 6-membered rings and then a 5-membered ring. And then there's various substitutions on those ring systems. And you can already see that, the Robinson annulation is quite useful for starting this fused ring system. And it was really an opening, salvo, if you will, into synthesizing some pretty interesting naturally occurring steroids and, of course, synthetic ones as well. So that ends our discussion for chapter 22. All right. Hope everybody's doing well, and reach out anytime you want if you want to kind of meet and go over some things, and we can do that via Zoom, or I can send out any kind of materials you may need. All right. Hope everybody's doing well, and have a nice weekend. Thanks.